这个刚好不行。哦，是无线的。Okay. Okay, cool. Okay, everyone, let's get started. Okay, first of all, good job so far. So last week we have the land following, and then we also have robotic vision, visual features, some detectors and descriptors to deep learning. So I think we have well. And of course, to run a DocuBot, I guess about Hopf transform. Okay, and system-wise, we also and we have assignment. Everyone can use, right? Okay, and more importantly, you guys can work as a team. I think this will be the most valuable part so far. Okay, this picture before. Okay. So Monica has been there in person, right? So maybe do you want to talk a little bit about it? 中文也可以啊。As Monica mentioned, a famous spot if you visit Boston or visit MIT. Yeah, and then the meaning is that there's a hydrant here, right? When you start to drink water, the knowledge, and then it's just like very water from the pipe. And in the beginning, you may feel overwhelming, right? So you feel that, the profession me a lot of things and the time to learn everything, etc. But I guess by now you guys are doing pretty well, and you guys start to know how to learner and try to find the important part and get the essence of what you want. Extremely for graduate students or seniors, right? Okay, and yeah, I have the same thing when I do my postdoc there. There are too many things to learn, and I cannot pretty well. But I do this kind of learning style become. And this is probably a little bit small for you guys, but okay. And today we will talk about some RANSAC and other and how can RANSAC do for us robot. And yeah, I had some more assignments, pretty easy, right, so far. And then the next assignment will be a proposal. Down some of them, the found first, right? And as a team, you guys have finished papers already, okay? And for the next assignment, you have about 2 weeks. And the last assignment will be something more in than land following. Okay, I will describe this short. Okay, and we have the Dread Festival, or somebody call it Rice Bowl, bowl. And we won't have the class on May 29 to cover innovation, some literature, your approach, and expected just 10 minutes, maybe 10 slides for each team. Okay. Well, some of this already, and for the event, that will be do some more exciting things. So I would assume that you get to know the repo pretty well by then, and then you are a capability of a ducky bar. For example, right now the ducky bar can only white line. For example, a ducky bar can yellow line bypass an obstacle. Okay, and in order to do those, you will need to know the OCW. And the better news is that our OCW is when you go to the OCW NCTU, and you will see our open to everyone. Okay, and please do go to NCTU. And some more exciting things. Next week we will have will introduce some perception for some how to process the point cloud and maybe do some. Okay, so questions so far?
Presentation. First May, we will have a demo on this day.
Okay. Oh yeah. Yes, you have. So that's a proposed in-class tutorial. It's different, but also the data were collected by PR2. The data collection, it lasts about 2 years, actually. You could see that the bottom left, that's the data center in MIT. And they use this robot to collect lots of data that we can reuse. For example, the laser scan on the base mobile platform, and also RGB and RGBD images, also a stereo camera. Actually, the size of the log files are huge. Actually, it's ranging from 1 gigabyte to 63 gigabytes. Otherwise, 63 is like, wow, it's pretty big. Data collection is by this PR2, and it's tailor-up. So someone just use a joystick and drive the PR2 around in the building. And you could see on the right-hand side over here, by those sensor data, some SLAM algorithm can rebuild the whole data center like this. In the second half, I show you like how to visualize the data first. So there are lots of them. For example, those depth camera, etc. For example, you could also use some tools in RAS so that you could visualize the data to get you a better way to debug or to develop your code. And since the PR2 has lots of sensors, so for example, a stereo on top, or maybe a connect mounting on the head, and also there is a planar light dot at the base. You actually need to know the relative transformations among those sensors in order to do some sensor fusion. By some RAS tools, you could also visualize the TF tree. So that's more like what's the for each joint. On the base, you may have a frame called base link, and on top of it, you will become a tree. And then on the base, you could think that, for example, the left arm or right arm, there are some frames about manipulations, or some frames about the sensors. So you actually need to know those relative transformations so that you can use all those sensor data and then control all these manipulators. So the second part of the lecture, we will talk about RANSAC. And actually there are lots of application or some like usage in computer vision and robotics with RANSAC. And it's an acronym for Random Sample Consensus. you have to remember two key ideas. The first one is like what's the inliers and outliers. And the second idea, it is an iterative process. It will run a few thousands of iteration in order to get good results. And you could see it from the bottom left. You could see 3D lines, 3D cylinder, or a 3D surface. And RANSAC has been used widely to process 3D stuff. So we have few steps. First, try to randomly select a seed, a group of points on which to base transformation estimate. Second, compute the transformation. 3, find the inliers. 4, if the inliers has sufficient estimates and do something about it. So actually we could quickly take a look at the example so that it will be much easier to understand. We will use just one sample in 2D, but process is the same when you do it in 3D. So suppose we have few points over here. So you could see that from all the points, the least square fitting will look like this. But this is not exactly what we are looking for. We want to reject some noise. We don't want to take the noise into account to find a line that fit our inliers well. So this is not exactly what we are looking for. Let's get started with RANSAC. Okay, so first of all, the first step is to select a minimum subset of points. For example, over here, we just select 2 points. And then our goal is to fit a 2D line over here. It's fairly easy that y equal to ax plus b. So we hypothesize a model here. It's a line in 2D. And the next step, we compute the arrow functions. For the rest of the points, we compute the distance from all the black dots to this line. Okay, and we have a summation of those. Obviously, this line, the first hypothesis, it does not did a pretty good job, and you have a huge arrow accumulated from those black dots. We could select a range of points not that far away from our model. Okay, so you could see that from the blue line, you could select a range of it, right? And then you could say all the points within this range, we will consider those as inliers. Yeah, that's pretty much it about RANSAC. So this is just the first iteration. And we will do it for a few thousand times. Typically, we repeat, we select 2 points, and we find a line, and then we calculate the arrows, and then we select a range of the points as an inlier. And then we try to verify that how close have we get a satisfied result or not. And we do this maybe one more time. All right, and once again, finally, we found a line like this. Okay, and you could see that this one is is pretty close what we are looking for. So if we do this one more time, maybe for this one, we get the larger arrows compared to the previous one like this. So this is essentially the process of RANSAC. You may think that this seems not very smart, right? You just have lots of iterations and you try to fit a line that get small arrows. If you repeat n times, you will kind of draw S points uniformly at random. And then you try to fit the line to those points. And again, find the inliers. If there are D or more inliers, accept the line and refit using all the inliers. Later on, we will talk about the pros and cons and compare to other methods. But first of all, just let you know that RANSAC has been used for many applications. For example, if you have 2 images, you take a photo of the same thing from different perspectives, and you want to match it or try to connect all the photos together. Maybe in your cell phone, and there is a function in your camera. you could hit the panel function, right? And then you could just slide it. This is essentially what RANSAC can do for you. Whenever we learn a new algorithm, we want to have some discussion about what's the pros and cons. The first part about robust to noise. Depending on the number of noise or the value of noise. Maybe it's something about the number of inliers and outliers. Maybe from a real world application. Suppose you have a 2D LiDAR and you have a LiDAR just scan, right? Have a 2D scan. And then you found a few walls as lines in 2D, right? But unfortunately, suppose there are many people walk around, and that will cause some occlusion. Okay, so what do you think about occlusions for finding a line in RANSAC? Okay, 假如说你有一个线段，对不对？ When we talk about noise, it could be you add something to it, or something is missing. Okay, so suppose you have a line. The ideal case is that you have all the points here, right? And if you add some noise somewhere, that will be some addition to this data. And the other scenario would be that suppose there are some occlusion. So the line like this, maybe this part is gone. So far we have been talking about inliers and outliers, and maybe we could also think of the signal and noise. This will come to the second questions. Will we get consistent results? So suppose we focus on the second part and assume that we have unlimited computation resource. So will we get a consistent result in the end? Suppose we run a very large number of iterations. Perhaps. Okay, cool. Yeah. So I think the number 2 and 3, they are kind of relative, right? Depending on like how much computation resource are available and how many iterations you could run here. How about last part? Some of you asked about what exactly this means. Essentially, suppose you have multiple lines in your environment. Will RANSAC compute multiple lines for you? Suppose we have 4 lines. And even that you found a model that fit one of the line perfectly, but the algorithm will still tell us that this is not the good one for us because it will count for all the points in the data, right? Some summary here. Let's see if those are consistent to our discussions. Okay, the first, RANSAC will be robust to outliers / noise if there are not too many. So I guess a number of outliers would be one thing to consider, or maybe the distribution of the outliers. The second good thing is that the number of hypotheses n is taken sufficiently large that RANSAC give very similar result every time. Okay, that's probably the second point. You do the iteration lots of times, and you will eventually get very similar result. Okay, but the downside is that the computation time grows quickly. Okay, and also with the friction of outliers and number of parameters. That means, for example, if you fit something in 3D, if you fit a surface, you will have 4 parameters, right? Or maybe a shape or circle or something else. And the other thing is that it is not good for getting multiple inlier structures. So we have learned about Hopf transform. Is there any advantages for Hopf transform other than RANSAC? 太多的话，线会变成另外一条。对。有可能。Remember that suppose a line and you put it in some like sine wave, right? And then the intersection of the voting will become one point here will become the line in the XY plane, right? One thing obvious is that for the last part, we have been doing Hopf transform to detect multiple line segments in Ducky Town. right? And for this, RANSAC won't be able to give us this. One good news in PCL is that there are many RANSAC-based methods available now. So for example, you could fit the line in 3D, fit a plane in 3D, or cylinder, or some other patterns. So in addition to 3D points, RANSAC is also very active in many applications. For example, one very useful technique will be visual odometry. There are lots of techniques we have already learned, and not everything. Today I will introduce you one of the library called FORVIS. This one, the input is a RGBD, it's a connect. Okay, but depth information is only used to get rid of some bad points. Okay, but the core of this algorithm essentially RGB. And this one is published in 2011. I still think this is one of very well written code as well as the algorithm. So I would like to introduce this one to you guys, and maybe you could use the code and run some data sets to compare some results, or put this in your application. There are a few steps in FORVIS, and the first one is image preprocessing, and this one is pretty much similar to any other algorithm like apple tag detector. So definitely want to smooth the raw image a little bit. So the pre-processing is quite essential. The second part is the feature extraction. We have introduced some of the features in the class in our first half. Corner, yes, exactly. Corner detectors such as Harris corner. We mentioned about Harris corner, but we also introduced some other corner detectors. Fast corner, exactly. Yeah, we have been introduced some of the feature detectors, and in FORVIS, actually, the FORVIS used the fast corner. And the reason is because fast corner is very fast. That's desirable if you put an algorithm on a UAV. And the next step, if you introduce some initial rotation estimation, for example, you use a motion model, or you use the IMU or something else, and it will highly constrain the search space. In the end, you will have to match the features from frame T to T+1, or if you have a stereo, that will be also some feature matching. Then if you have some initial rotation estimation, that will help you to speed up. And the next step is to do the feature matching. These steps, I guess some of you still remember the descriptors. SIFT, great, excellent. And what's the dimension of SIFT? Okay, add 8 directions. So essentially compute the gradient directions as well as the magnitude, right? And then like cut it into bins. Yeah, and then I think in the end the dimension is 128. Is that right? Okay, great. So essentially when you get a feature point, corner for example, you need to some way as a descriptor, so that when you see the same thing at T+1 in the next frame, you will be able to match them. The next step, that will be something we just talked about. For example, we would definitely want to find the inliers between 2 frames in order to do this match. And finally, those matching could give us enough information to estimate the motion of your robot. Okay, so let's take a look at each step in detail. So first of all, the pre-processing, Gaussian smoothing is quite standard. And Gaussian smoothing will help us to get rid of some like salt and pepper noise. How about Gaussian pyramid? What's this for? So anyone remember like why would we want to calculate a Gaussian pyramid for input image? Well, so suppose you have a camera and you see the same thing in this distance, it's probably very close. So the scale, it will be pretty big, right? But when you see the same object from far away, okay, you will see that the same object become smaller and smaller, right? And this is also an important proof for us to estimate the motion of the robot. Okay, so doing Gaussian pyramid will help us to get this multi-scale information. And the second step, just like what we mentioned, computing fast corner or use other corner detectors is a very typical way to get the features. So fast shift, surf, or high-risk corners. They are very popular corner detectors. Typically, you will get, for example, for fast corner, you will typically get more than 2,000 points in one image. And you also do this in multi-scale. So like for example, Gaussian pyramid, you have, this is the original one, and when it go up, it will become smaller and smaller. And essentially, we want to extract the features in all scales. Here, typically, we will need maybe 2,000 or more feature points. In FORVIS, the input is a Connect RGBD camera. But here, the depth information is only used for feature selection. So for example, how many of you have played with Connect sensor before, or structured light sensor? If you play with low sensors, you will know that Connect sensor cannot see something black or something reflective, like a glass or mirror, or maybe some like water, anything reflective. Because the projection of the structured light won't be able to get the things back to the depth. And with the depth information, we could actually get some more features. We could reject something we don't really want to use. In the algorithm, it also do something interesting, something called a uniform distribution of features. So essentially, if you have an image here, it try to cut it into a few bins or buckets, okay? And then, does anyone know why the algorithm want to do these steps? Why would we want to calculate like a uniform distribution of features? Some hint is that now we want to estimate the motion of a robot, right? And then we try to get the features from two images, maybe frame T and T plus 1, for example. And we want to extract the features and do the match. The algorithm try to do one more step to cut one frame into a few bins. So can anyone figure out, like in what scenario this become a must-have for this algorithm? If we don't do this uniform distribution, in some case, we will get a wrong robot motion. Let me show you, maybe give you a little bit more hint over here. You can see that in this image, the algorithm tried to cut it in different bins, right? So one reason might be that it could speed up the computation, especially that if you have an assumption that your vehicle, what's the moving speed and the frame rate, you could have a constraint that this point could only move in a few range, right? You could constrain the search. This is one reason. This is another reason. So suppose you have an image like this and you extract lots of features, a very condensed area. For example, you could see there are lots of text or license plates in a very small area because the richness of the features, you could see that lots of features will in this small area. If your vehicle is behind the other vehicle here, And this will kind of get the wrong robot estimation because all the key points, all the features is within a small area. And in this case, the robot may think that I'm not moving at all because it's kind of follow another vehicle which take pretty much all the features in a small area. But you can see that there are some other features, for example, the trees or some other features on the ground. So if you cut it into a few bins or buckets, you could actually use this uniform distribution to get a more accurate robot motion. Okay, instead of that large van steals all the inliers in this situation. All right? So this is also kind of relevant to our discussion today about inliers and outliers. And the next step is the initial rotation. If we know this rotation, this will allow us to constrain the search window so that we could have a faster calculation here. And in fact, we could also use an IMU, for example, to fuse two sensors, get a good initial rotation estimation. And the next steps, we will need the descriptors for each feature location in order to find the good matches. In this case, that's the blue lines. Or there are also some bad matches shown as red. For the descriptor, for example, SIFT is 128 dimensions. Okay, and I think we also introduced a briefed descriptor. The brief descriptor will use less bytes to describe a patch. For frame T and T+1, it could calculate the matching score. And let me ask you a question. So for a descriptor, we want the descriptor to be invariant to what? Yeah, let me show you, maybe show you this. Okay, so we have learned about SIFT. We have learned about brief. We want to find the same feature again between frame T and T+1. Do we want it to be rotation invariant? Do we want it to be like perspective transformation invariant or scale invariant? So that may be like this in this dimension, right? Suppose your descriptor is a scale invariant, and you see it from here, you got this feature, and you see it from here, you got the same feature. So actually, in this case, we want it to be scale invariant, right? And rotation and perspectives. What do you think? When you see the same feature from different perspectives or different rotations, you want to match the same point between frame T and T+1. Yeah, so you could see that there are lots of blue arrows pointing left. Okay, and the middle one is more like the arrow is pointing outward, and the right one is about the rotation. In previous slide, we talked about rotation, we talked about perspective, and also maybe the distance from the object. So I think over here, suppose we can track the same feature and in different rotations. This will be this case, okay? Or this case is like this, okay? And the left-hand side, yeah, is something like this, okay? So that's the tracking part. And there is also another trick to speed this up. If you try to match the features in this scale, so you can imagine that some bigger feature could be tracked in a smaller scale. Then we don't need to dig into the high resolution one. So for example, in our Ducky bot, we have 640 by 480, right? And if you can track some features at a smaller scale, for example, 160 by 120, and you won't need to use that much computation for the high resolution one. Actually, FORVIS also supports stereo matching. That's fairly similar to the temporal one, and this is like a special one from just a little bit disparities, left and right. And this is the temporal matching. Great, suppose we got the features and we have the descriptor to do the matching. And we actually need to find the inliers, because the matching could be, suppose you have 2,000 points, you want those points to match it in the next frame nicely, and as many points as possible. Unfortunately, because the features, they are kind of a small patch in the image. So it's very likely that the feature will get the wrong match somewhere, okay? And here we could actually, suppose we got 1,000, maybe 500 matches between those two frames, and we could use RANSAC to get inliers and outliers, okay? So the process, you're already familiar with this. We want to select n out of m data items at random. So in our toy example, that's just 2 points, right? Here, the minimum stat is 3. And we want to estimate the parameters, okay? And that's the pulse from t minus 1 to t. And we find the number k of data items that fit the model, called the inliers. That's for our toy example. That's something within our predefined range. And then we repeat this for a few times, maybe 100 or depending on the problem. Okay. And we calculate the refined model using the 4 inlier set. Okay, and finally, we got the inliers, okay? And we could actually use some way to estimate the final motion. And this is Professor Hong. He's still in MIT, this professor, almost retired, but still there. That's one of the famous way to estimate the motion, okay? And the basic idea is that maybe we could see it from a different perspective. So suppose we got 3 landmarks, and in previous step, that's actually the features we found from t to p plus 1. For example, this is minus 1 and this is t, okay? And we check the same landmark, and we could actually estimate the camera pulse in 3D. So far, we have very quickly introduced step 1 to 6. The good thing is that the code is open source, and I have been using a FORVIS library for various applications. Yeah, you could take a look at the detail in the paper here, and also the code. And the good news is that this is also available in ROS. If we could just compile the code, make, and play with the Stata data set, you may be able to play with the algorithm. In FORVIS, we already introduced many of the components, but not everything, right? But I hope this will still give you some insights about, like, for example, in this work, it actually used many of the computer vision and robotics techniques and put them together as something very useful.